Okay, today's topic is the entrainment and multi-stability of the p53 oscillator in human cells. Let's start with reading abstract. So we will read. Do you have any comment about this abstract? Nothing.
No gap.
Yeah. There's no explicit gap sentence here.
It's old school. Introduction, here's what we did.
Yeah. They explain what they did, but there's no research question.
Did they newly develop the mathematical model, or is there any research about this mathematical model?
Of course, there was many mathematical models describing the p53 oscillators, but with the model and experiment, they show that some dynamics theories in dynamic field really occurs in the p53 system.
I think it's the first time that's seeing the last sentence.
Oh yeah, I didn't see.
I've never seen that kind of sentences, even though we could have been did this journal for many years.
Yeah, me too.
Is there a specific reason for and
I don't know, I think that some reviewers ordered, maybe, because any papers in the published from this group didn't write this sentence. So I think during the revision process, maybe they added. Okay, then let's move to the So first, the entrainment is the phenomenon in which one oscillator adapts the period of the another oscillators. The circadian clock is one of the examples. So circadian clock is also oscillator, but everyone's internal period of circadian clock not exactly 24 hours. So if we confine the mouse to some dark cage and we measure their activity, because their internal period is not exactly 24 hours, their activity cycle delayed day by day. But if we give the 12-hour light, 12-hour darkness, so another oscillators, their activity is fitted to the external oscillator. This phenomenon is called so we call this the the circadian clock is entering to the light dark cycle. As well as circadian clock, the P53 is also oscillatory systems. In the P53 oscillators, some DNA damage such as the radiation triggers oscillation via the negative feedback loop. In this loop, the radiation, the DNA damage activates the P53 and then it induces the transcription of MDM2. And then MDM2 inhibit its own transcription by inhibiting P53 for transcription activity. So with this negative feedback loop, the P53 oscillators can generate rhythms with about a 5.5 hour period, like this. If we give some radiation, it starts to oscillate like this.
What is FC here? Fifth is then.
Oh, let me check. I didn't check that. FC is the
Fluorescence. No.
fluorescence.
No.
Voltage change. Voltage, yeah, so relative amount.
I'm sorry, but what is P53?
P53 is the protein,
Protein.
respond to the DNA damage to recover the damage. So if we give the P53 is called by the guardians of the DNA. So if they detect some damage, they start to do something to make a decision. Apoptosis or
Then MDM2 is also protein?
the target of P53, the constructing this negative feedback loop. So P53, activate the transcription of MDM2, and MDM2 inhibits the P53. Of course, as well as MDM2, there are many target genes of P53, but to construct the negative feedback loop, I introduced the MDM2.
Okay.
So anyway, the P53 also oscillator. Then we wonder, is that it in the P53 oscillator entrainment, or whether entrainment occurs? Then we can give a oscillatory signal like this. Nuclein is the component which inhibit the inhibiting activity of MDM2. So it activates the P53. So we can give this nuclein like periodically. Then if we give the nuclein like this, the activity of the level of P53, the rhythm of P53 entering to the nuclein rhythm. And if we change the period of the nuclein rhythm, it is entering to the nuclein period. Even each internal clock have a period of 5.5 hours. So P53 oscillator is entering to the nuclein pulse. And to understand it more clearly, rather than the rhythmical signal, they just gave a single pulse. The easier signal to interpret rather than periodic signal. So if after giving DNA damage, they start to oscillate, but in the population level, their needs decay because they have no signal, so their period, their cycle is, their pages are changed and default between cells, so their mean become decay. But after single pulse, they live synchronized. So, what interesting thing is that because in here every oscillator shows the different phase. So some cell get the single pulse when they are peak, and some cell get the neutral signal, pulse signal when the level of p53 is middle of oscillation, and some cell get the single pulse when they are nearly through it. So what the interesting thing is that regardless of their oscillation pace at the time of addition of a single pulse, individual cell shows the immediate peak. So if we get the mean of each cell, they shows the synchronized peak from the single pulse. So this phenomenon is called by the phase resetting. Due to the single pulse, their phase is resetted to the peak. So to determine the requirement for phase resetting in the P53, so which condition they can, well, which condition, under which condition, to investigate which condition they can get phase resetting, they constructed a mathematical model. So in this model, the P53 is produced with a rate of K1, and it decay rate of K2, and it destabilized by the MDM2. This term describes the inhibition by the MDM2. And P53 produce transcription of MDM2 mRNA, and it decay with the rate of K5, and mRNA translated to the MDM2, and it inhibits the P53's activity like this. And effect of Newtonin is reflected to the K2 terms. So without some pulse or the signal, the K2 is the constant. But if we want to give some pulse at the time of t on, we can change the value of K2 at the t on. So if we see this equation, this term is 1. So this term is 0 at the t is t on. So it is changed to the K2 1 from the K2 0. And then as time goes, it converges to the K2 0 1. So it shows sharp exponential peaks at the t1, time t1. So they reflected the neutral impulse with this function, the parameter K2 as a function of time.
In the MDM2 mRNA linear differential equation, its production is proportional to P53 squared.
Yes, squared, nonlinear to make the nonlinearity. And as I know, the P53 forms heteromer, but they use this square.
Okay.
Anyway, they have some properties. So.
Okay.
Yeah, so they used this OD models. And fourth, in the model, at the high neutralin concentration, so 1 micromole of a neutralin concentration, they were predicted showing the immediate peak in the, regardless of their initial phase, as we observed. However, in contrast, a low neutralin dose or very weak resetting was predicted to occur. So compare with this, it shows the immediate sharp peak, but the Hato peak decrease, and at the low neutralin dose. So we can conclude that the magnitude of the stimulus, not the pace of the internal oscillator, so when we give a stimulus, is a key in determining the P53 internal oscillator to reset. So for phase resetting, yeah, magnitude of the stimulus is important.
Can I look at that again? Yeah. I didn't- What am I supposed to be noticing here again? The left is a stronger
Yeah.
perturbation.
Yeah, right.
And what does that mean again?
So strong, yes, the strength of the stimulus is key, the key determinant of the phase resetting, rather than the phase where rather than phase of internal oscillator. Because regardless of whether the signal given, they shows the phase reset when the nuclear concentration is high. But it becomes weaker if the nuclear concentration is.
What's equal here in the right one?
Sorry?
What's equal? Sorry, I mean, I understand you're saying that the strength of the perturbation matters, but I'm not seeing what, am I supposed to be looking at the blue curve? What am I supposed to notice about that?
Yeah, right. So they increase like much.
Yeah, it's a moment of the perturbation.
Yes.
They both look like they settle back into an oscillation.
Yeah.
Left and
Because,
right, they both oscillate. What's the difference?
right before come back to the sustaining oscillation, the response to the nuclear concentration, very different. The stronger concentration, the strong change, the larger change.
Okay, it takes longer
Yeah.
to return, where this one
Ah.
looks like a regular oscillation sooner.
Rather than the time returning to the limit cycle.
I mean, that's what phase resetting is.
So we.
How long it takes to
So phase resetting is in the population level, we average, imagine that we average about these 3 time series. And if their peak is stronger, their average time series will shows the large peak. So it means the stronger phase resetting.
Okay.
I think we need to focus on the middle, both figures.
This one and this
Yeah,
one.
so the dashed line part, left part, like even though the stimulus is applied to the through of the oscillation, the blue curve goes here in the middle.
Mm.
But for the right side figure, only increases not so much. I think that's the key difference.
Yeah, as well as middle one, but their increases.
There's two conflicting ideas. Phase reset. Phase resetting is you have a perturbation. What is the phase shift after t goes to infinity again? Right? You perturb and then it'll go back to a regular oscillation,
Yeah.
but the phase will be shifted relative to the oscillation before the perturbation.
Right.
That phase difference is the phase resetting.
Yeah.
Right?
Yeah.
Then they're also, so at the time you apply the stimulus,
Yeah.
you've got a whole bunch of cells that are all in different, they all have different phases,
Yeah.
right? So where in the phase a given cell will be when the perturbation is applied is random across the cells. So what happens? Will the phase be shifted forward or will the phase be shifted back?
They investigated the PRC.
So that, then they average
Yeah.
over all the random phase changes
Right.
in that picture, right?
Yeah. And
So
But after single course, they think again. So I think that
they briefly, maybe you can think of it as synchronizing. If you do a strong perturbation,
Yeah.
then the mean will be shifted towards how do I say this? They sort of transiently will be slightly synchronized in the phase,
Yeah, right.
instead of completely spread out in phase.
Oh, yeah, it occurs here.
So that would depend on the strength of the perturbation. Stronger perturbation means you're gonna get a stronger transient condensation of phase across all the cells, I guess you could call it.
Yeah, exactly. That's why it shows the stronger change in the stronger thing. They also page receptive but weaker.
Like,
Okay. Yeah, and then these model predictions can be validated with the experimental measure, the page transition curve PTC. The page transition curve is measured like this. So we have a sustaining oscillation, then we can give a stimulus. Let's say that the peak point is the page 0. Then we can give stimulus at the page 0. Then the rhythm will be perturbed. Then we can measure the change in final page. And then we can give a stimulus at the different initial page. So for example, if the peak was 10, this is maybe become 10 if this period is 24. So each page also changes differently. So anyway, we can measure the theta f with respect to the theta I, the time when we gave the stimulus. Then we can draw the plot like this: the initial page theta I versus theta f. So let's see the strong stimulus. The black dot is the model and X is the experiment point. They show the similar intensity. And in the case of the strongest nuclein concentration, regardless of the initial phase, it goes to the same final phase. So this flat plot means that phase is receptive. But when the nuclein concentration is weak, some cells shows the non-receptive state. So with the PTC, you can observe that as the nuclein concentration becomes stronger, the phase is strongly receptive.
Can I have a question?
Yeah.
So the final phase theta f is defined by the
Yeah, phase with respect to the internal period.
not perturbed period.
Yeah, in a perturbed period. But although it perturbed due to autonomous oscillator
Yeah.
comes back to each period. If we have no intensity here.
Or
so in the limit where the strength of the stimulus goes to 0, it should be just a perfect line, right? Slope 1
Yeah.
from 0 to,
Yeah, to 0.
no,
To the slope.
just the diagonal line, right? In the other limit, where the
to
strength of the
if
perturbation
it
goes
goes
to
to the
0.
Yeah.
The beginning phase is the same as the end phase.
Yeah, it maybe.
Right, so it should just look like a perfect straight line.
Yeah, in the under the 25.
But it's also a periodic function, so that's why you get that weird jump up to t in.
Yeah. Yeah, it will be. Can I move next?
헷갈렸는데 셀 타입가
음.
그냥 저 위치인 거예요. 그러니까 0에서 T 트윈지 피리어드
파이널 페이지 이제 예를 들어서 이제 PD 0시에 썼다고 하면 지금 이제 PD 어디로 옮겨가면 예를 들어서 2시로 예를 들어서 뭐 2분의 파이로 옮겨가다가 2분의 파이를 지킬 거고
근데 지금 힌트에 거의 비슷하게 다 지키는 거 같아요.
어디요?
그러니까 뭐2 마이크로
아,
셀 때?
this one. This one.
Yeah.
To the same final page. So regardless of the initial page, then it goes to the same page. The page is resetted whenever we gave stimulus. Yeah. This one and this one goes to the same page. The yellow code. So we can observe the phase resetting with the phase transition curve. And then we will calculate the synchronization method with the level of synchrony. The level of synchrony will be calculated with like this. For example, at the gray line, we can determine the pace of each rhythm. And depending on their pace, we can draw unit vector with the direction of that pace. So in the case of well-synced case, every rhythms direct the same direction, in the same direction. So if we calculate the mean vector of these four vectors, when all of the rhythms are well synchronized, the mean vector, the length of mean vector nearly 1. And when they are desynchronized, their length of their mean vector nearly 0. So this length of mean vector means indicate the level of synchrony, and this plot is called by the Rayleigh. So frequently used to observe the synchronization level in the circadian clock or oscillator. Yeah. So red one is the initial phase in the cell. So and then we gave the pulse at every initial phase. Then final phase is changing depending on their initial phase. But when Newtonian concentration become stronger, they concentrated some point. So if we calculate the level of synchrony, in the case of weak Newtonian concentration, it shows the weak synchrony. But when we get the higher Newtonian concentration, it shows the stronger synchrony. So it supports the phase resetting. So increasing Newtonian concentration, led to the increased synchrony, and it suggests that the higher Newtonian concentration, reset phase. And then we can interpret with the PRC as well as the PTC or the level of synchrony. The PRC is similarly measured with the PTC. The PTC measures the theta F with respect to the theta I. But PRC draw the delta theta, so change of the final phase, the difference between final phase and initial phase. So theta I versus delta theta. So depending on when we gave the stimulus, how rhythms page respond. Also to interpret this PRC depending on the Newtonian concentration, let's see some equation first. So in this equation, so we will search the condition for the one-to-one entrainment when entrainment occurs. So we will define the set time, the Poincare as the page of the internal oscillator after n pulses. So in this plot, if this is the set time, the next cycle it will be the set time plus 1. And this equation is that during the one period of external signal, the set time goes to the next page, the time goes to t as much as the the external period, and then by the effect of some stimulus, it moves as much as the PRC theta n. So next page theta n plus 1 becomes theta n plus PRC theta n plus the external period. And to get the page, we apply the modular t internal period t. So when the external period and internal period is similar, so each modular will be just the difference with the t external and t internal. So to be entrained, the page should not change as the cycle goes. So there should be exist some fixed point theta star. So to calculate the condition for the fixed point, we can switch the theta n plus 1 theta n to the theta star, some fixed point, some fixed page after entrainment. Then we can derive the equation. Here's theta star is the difference between the internal period and external period. And then to get the stable point, it should satisfy this condition. The relative change with respect to the change of theta n, the theta n plus 1 should be smaller. As the change becomes smaller, it will converge, so it means the stable point. So because we have the equation, we can calculate the d theta n plus 1 over d theta n. Then we can get the 1 plus the absolute value over 1 plus PRC prime. And it should be smaller than 1. Then we can derive this equation. So the condition for the one-to-one entrainment is that the slope at the steady state in the PRC should be between the 0 and minus 2. Then let's go back to the PRC again. So this is the slope 2. This is the slope 2. To get the one-to-one entrainment, it should satisfy this condition. So red point is the point can get stable one-to-one entrainment, and black point is the unstable one. So if we see the condition, we can get the one-to-one entrainment as the neutralin concentration become higher in the wide point, we can get the one-to-one entrainment. So Pierre suggests that the stronger input, the more page shifted, and it can tolerate to the achieve one-to-one entrainment. So we can observe it from the Pierce. And then next to address whether p53 oscillation could be entrained to the external periodic neutralin. So p53 oscillation observed. So they made a system where, so after the DNA damage, they start to oscillate, and they give up another oscillatory signal with the neutralin. So we can see the entrained signal in the zone 2. After that, in zone 3, they made this system. So by changing the external period to entrain, they observed the change of the p53 readings. Then the OD model closely predicted the one-to-one entrainment across the every neutralin period. But as we can see, as the internal period of p53 was the 5.5 hours. As the external period shows larger difference with the internal period, it is hard to entrain. And in the individual level, the greater heterogeneity in the p53 oscillation in response to the 5-hour Newtonian period, which shows the large difference with the internal period. Shows compared with the 4-hour period, showing the small difference with the internal period. So as the external period shows the larger difference with the internal period, it shows more heterogeneous readings.
It's 5 hours,
Yeah, internal period. Yeah, 5.5 hours. So it is close to the internal period, but this is the far from the internal period. So as you can see, when the internal period is external period is close, it shows the similar rhythms, so synchronized rhythm, but in the case of a larger difference, it shows the heterogeneity in the rhythms. So external input with the period far from the natural p50 oscillations, the 5.5 hour increases the self-self variation. And in the case of 11-hour period, so quite far from the internal period, if we increase the concentration little, they shows the more synchronized rhythms. Even their period is different, quite different from the internal period. So this is called by the frequency pooling, a phenomenon where the natural oscillators frequency is pulled towards the frequency of external oscillators when the magnitude of signal of the external oscillator is strong. And we also can observe the as well as a 1-to-1 entrainment, 2-to-1 ratio entrainment. For example, this is the single cell A shows the 1-to-1 entrainment because it shows only one peak per one cycle of entrainment. But in this case, during the one cycle, when the external signal goes one cycle, the internal signal shows 2 cycles. This phenomenon is called by the 2-to-1 ratio entrainment. So, and you can observe the P to the Q period locking, the phenomenon where the entrained oscillator goes through the P cycle for every Q cycle of the external signal. So 2-to-1 entrainment also observed in the p53 cells. When the Newtonian period is close to the natural period, so 5.5, so 4 and 7 is close to the internal period. Then ratios, if we calculate the distribution of a period of each cell, they shows the unimodality. But as the period becomes the external period becomes far from the internal period, they shows the bimodality or trimodality. And it consists, so it means that it is getting 1-to-3 entrainment. So, and we can analyze this with the power spectrum by applying the Fourier spectrum. Then it consistent with this distribution. So so unimodal peak, bimodal peak, trimodal peak, even in the frequency domain. And model simulation, so this is the experimental one. So model simulation also can observe this phenomenon, like this, the 1-to-2 entrainment or the 3-to-2 mode. For example, red one shows the 3 cycles during the cycles. So this is the 3-to-2 entrainment. So model can reproduce this phenomenon, and we can draw depending on the period and versus the Newtonian concentration. So magnitude of external signal, we can map the entrainment state like this. So we can observe the one-to-one, we can get the one-to-one entrainment as when the neutral period similar to the internal period. And as the neutral concentration become higher, it can entrain to the in the wide range. So it looks like the tongue. So this map is called by the Arnold tongue map. So yeah, it can entrain well in the near the internal period, and as the magnitude of stimulus becomes stronger, the range of entrainment becomes wider. So it looks like tongue.
So no color means no synchronization?
Which color?
White color.
Oh yeah, white color maybe, yeah, no synchronization. Maybe chaos or all without entrainment, just go with their own oscillation. Right? Because in this case there's no stimulus, so entrainment signal. So it will go with their own rhythm. So no entrainment. And if we simulate OD with the Langevin noise, the stochastic simulation, we can observe some change of mode. So it was first the 1-to entrainment, then it switched to the 1-to-2 entrainment under the existence of the noise. As the level of noise becomes stronger, it switches more frequently. So it cannot observe in the deterministic system because it is entering to the some dynamics. It cannot change the mode, but due to the noise, it can be switched mode from the 1-to to 1-to-2. And period doubling was observed. Then this model prediction can be validated with the experiment. They also observed this model ping or the period doubling with the p53 oscillation. So we can expect that the cell is very noisy system because their mode is changed in the cell without any stimulus change, only due to the stochasticity. So we can classify every cell with the entrained one, period doubling one, or the model ping one. But there are some cells cannot classify one of them. So there are some unclassified cells, the purple ones. And if we measure the peak to peak distance, so this distance for every cycle, then in the case of a 1-to-1 entraining, they concentrate to the 11 hour because their entraining signal is 11 and they are entrained to the external signal. But they are more spread. Their distance between peak very randomized. So they hypothesized that such wide spectrum of frequency results from the twice undergoing chaos. So what's the chaos? Chaos, the dynamics which even two trace start from the similar initial point, the trace is completely different as time goes. So this is the example. So experimentally measured. Even the red one and black one shows the similar trace initially, but they both completely shows the completely different time series as time goes. And model also can generate this chaotic phenomenon in some parameters. And this chaos can be measured with the Lyapunov exponent. Lyapunov exponent is the draw minor. As time goes, we can measure the distance between these two traces, and we can draw it it's this distance between two trays with the lower scale. So each slope means that how exponentially fast become diverge between these two time series. So if the slope of this plot is positive, as the slope of this plot is the Lyapunov exponent, and if Lyapunov exponent is positive, it means that they diverge. So it means the chaos, because even they start from the close point, they completely goes to the completely different trajectory. And in other words, if the Lyapunov exponent is the negative, it means that they converge. They converge. And if we draw the phase plane of this, we can observe the strange attraction, meaning the chaos occurs. And this is one of the well-known cascades which goes to the chaos from the entrainment from the period doubling and chaos and one-time interactions. If we draw the peak of the amplitude, initially it shows the period one because but as the magnitude of external signal becomes stronger, it shows the double period and warp period and goes to chaos and finally entrainment. So this theoretical phenomenon is observed in the p53 system experimentally. So based on the mathematical dynamics theory, they observed this phenomenon with the in real cell human cell systems. Thank you.
So the final slide is simulation with noise, I mean model with noise.
Oh, without noise.
Without noise.
Yeah. Because it is just the bifurcation, period doubling or the period force. They just change the parameter. Because if they give the noise, it can be occur such as the phenomenon such as the mode hopping. So it can be switched to the period force and period force.
Yes.
So there is no noise in this simulation.
Ah, okay. In classification of the entrained period doubling mode opening on class 5,
Yeah.
how did they do that?
They make their own algorithm too. They compare the height of a peak, and then, for example, the period doubling is repeated two different peaks in each cycle. So and then trend shows some sustained peak. So which the difference between the peak of each cycle they classify. If it is sustained, it is entrained, or biorhythmically changed, it is the period doubling. If the randomly changed, it is model peak.
So the green and the blue,
Yeah.
those are their algorithm detecting.
Yeah, peak.
So what about all the other little peaks in between?
They have some standard, it was at least 30% of the previous people. Yeah. They have some standard. I don't remember it exactly.
Kind of gets a little fuzzy what's just a fluctuation and what's a true peak, I guess.
Yeah, it is the difficult problem.
That one right there kind of looks like a peak to me.
This one.
Yeah.
Yeah, so yeah, in this stochastic data, it can be.
So it may be just unclassified because it could be noisy, not really chaos.
Yeah, it might be.
It might
But anyway, they compare the trajectory.
Did they fit the mathematical model to the data? Or how
Not
did
just the
Just-
qualitative change.
okay. They just randomly choose the parameters?
They just changed the neutralin concentration. But some standard parameter. I don't know how to select it. They did not describe. They published the exact value of parameter, but there's no method how they get parameter.
Could you go to the slide of Langevin noise simulation?
Langevin noise simulation. Yeah, this one.
So yes. So Professor Newby, it reminds me of a third kind of metastability. Is it? Do you think this one?
This is complicated though because it's not a time autonomous system. So being driven by an external
Noise.
periodic force.
Yeah.
So I think what you're seeing is something that is qualitatively, that's like metastable jumping between different different steady state behaviors. The analysis would be difficult because of the periodic forcing.
I see.